You're welcome to our seminar on CPD resources for physics teachers, for teachers of junior cycle science, and for teachers who want to use digital simulations, particularly in relation to physics experiments. This seminar is presented to you by myself, Professor Geraldine Mooney Simmie. I'm the STEM professor here at the University of Limerick and the director of EpiSTEM, a research centre dedicated to STEM education. And I'm joined here by Dr. Vo Van De from Vietnam originally, and who's here now with us as a postdoctoral fellow here using an Irish research scholarship for this particular work. So we will now introduce you to the digital simulations. So an outline of the presentation is just to welcome you as science teachers on board the seminar, to give you some rationale behind the digital simulations, the thinking behind it being inquiry-oriented science education, and another powerful pedagogical approach to inquiry-oriented learning in the science classroom. And then after I have done that rationale at the beginning, then Dr. Vo Van De will take on and do some demonstrations of the actual simulations we're inviting you to take part in. And then we will show you how we want this to be a research project where we're asking you for you and your students to take part in some of the simulations and then to complete surveys that take no more than 10 minutes. We're particularly inviting you to take part in the research and to complete the research for us because it's original to Ireland. It's the first time we've had the physics experiments that are directly connected to the national curriculum here, and it's the first time that they are actually being put into digital simulations. So we are inviting you to please take part in the study and to reply to the actual study. And for the question and answer session, we'll give you some emails so you can come back in contact with us if you need more help. So before I begin, I just want to introduce you briefly to EpiSTEM. That's our national centre here for STEM education. It's a research centre located here in the School of Education in the University of Limerick. We have over 1,500 student teachers here with us every year, and they're doing their 4-year undergraduate teacher education programme or a 2-year PME. And we have all the STEM subjects catered for. So we've the sciences, we've the mathematics, we've the computer science, and we've engineering and technology subjects as well. We also have designed a number of research-led projects that are here funded by different organisations, including the Irish government and European projects. But along with those, we have CPD resources designed that are aligned with the national curriculum for science education that follow the guidelines given to us by the National Council for Curriculum and Assessment and from the Department of Education and Youth. So more recently, we have set up an online EpiSTEM Academy of STEM teachers. We have a number of science and physics booklets here, physical booklets that you can get if you email us and want them for your library or for the students. And we also have a lot of CPD resources under the heading of science in our online repository on the Academy. You can enter that by just clicking on our website, epistem.ie, www.epistem.ie, register for being a member of the Academy, and you can download hundreds of resources free of charge. We've designed them for the busy teacher. They can easily be adapted for your classroom. We hope they'll be useful to you, and we hope at some point you'll come back and let us know how we can improve on them. So first, to deal with the rationale behind our digital simulations. Well, they're connected to an inquiry-oriented approach to teaching science. So they're aligned to the national curriculum in Ireland in relation to junior cycle science and senior cycle science, and in particular in relation to the area of physics. So the focus on this particular slide is in relation to a systematic inquiry, a review that Vo Van De and myself did where we had published, and we're looking at what are the different features and what's going on around the world, and how is scientific inquiry defined in the science community. And it's defined as having a certain orientation to experimentation, a conceptualization of how you go about doing a science experiment, and then how you approach a scientific experiment, and then how you draw conclusions and reflections. So, for example, with regard to a school student, they might be talking about coming up with a critical question, making a hypothesis about it, then going off testing that experiment, that hypothesis through an experimentation approach, gathering and interpreting data, reaching a conclusion, and coming up with a way of communicating it. And then if they reflect on that, they might find that they could have used better tools. They might have made a better hypothesis. They might have found their predictions and their results were rather limited, and that they might need to repeat the process and come up with a better way of doing the scientific inquiry. So what the systematic review of the literature showed us was that scientific inquiry competences in the literature around the world are devised out and designed out to be 4 major headings. The headings are formulating the question and doing the hypothesis, designing the experiment, analysing the data, and drawing the conclusions and final explanation. And as you can see, each one of those can be broken down into separate subheadings. So we've focused for the most part on the subheadings that are marked there in red. So formulating the causal question, setting up the experiment, measuring the dependent variables, changing them, doing the experiment, being able to interpret the data, and finally arriving at some kind of reasonable explanation or conclusion. But understanding that that often leads to better questions and to a process that's iterative, and it's not so straightforward when actually done in the real world of science. But this is what our research has shown us. So what we have actually looked at here is the advantages of digital simulations. So we have looked at the literature and looked at how digital simulations can be a wonderful addition to hands-on experimental work. They're obviously, in terms of safety, they're safe to do, that students can do them on their own laptops. They've been found to be motivating for students. They have found to actually work in terms of helping people to get assessment of their scientific inquiry competences. So there's been a lot of advantages found in the literature in relation to the application of digital simulations in science and across physics. So what Dr. Vo van de and myself have been doing is been looking at how we create these packages of digital simulations for you and use that inquiry-oriented competences and the research coming back around motivation and how to design the tasks. So what has been done here is that we've already done the analysis in the literature, we've designed the concept, and we've created the prototype. So we've looked at the Irish curriculum, we've looked at the physics curriculum, at the junior cycle, at the transition year and senior cycle in physics, and now we're inviting you to give us the feedback. So to do the research for us for this pilot study that's very important for the future of physics education in Ireland and for the future of digital simulations being a part and parcel of the science curriculum. And then from your feedback, we'll be able to see how these are being integrated into the science classroom. And did you find our teaching guidelines and materials useful? And give us the evaluation so that we can continue to improve this approach to science education.
Next, I will demonstrate some digital simulation for you that we developed. First, I will introduce the simulation we call Geraldine motion. In this simulation, we want to explore the linear motion of the Geraldine with acceleration and this acceleration or content velocity. In this simulation, we also help you understand the variable shape of velocity time graph. We can show you some functions of the simulation. The simulation here, you can see some control bar and display pattern. In this, there are the information of simulation to tell you how to use the simulation, and this is some basic pieces background for simulation and material we assemble for you use the simulation and real feedback. Now we will play. In this simulation, you can see the graph of the motion of Charlie in the inclined plane and in the flat plane. Here you can see if we change some condition like we change block or we change mass or grass, the motion of the Charlie will change. We can see the graph here. With condition different, you can see different the curve motion in that. Next simulation I want to introduce with you is Hooke's law. In this simulation, help students to evaluating the relationship between attention of the speaker screen and the apply fault. With simulation, students can fill the table, and based on the table, they can draw the graph you see here. Yes, this simulation I introduced with you the information of the simulation and basic knowledge background about this, and the learning material. This is kind of feedback. In the simulation, we can train the screen in by this here, and we can measure the mass with the scale. Yes, we can measure the mass like that. Yes, we can handle the mass on the screen to observe its attention. Yes. Now, for example, in this we can measure adjust the ruler to measure the attention of the screen here, and then we can record the attention with each kind of mass, and we can fill the table as you tell you earlier. After that, student can draw the graph based on the data. Next simulation package I want to tell you here is a limit trend. This is we want to explore the factor that affect limit trend. The factor of human activity, for example, carbon emissions, deforestation, and renewable energy on the global warming. In this simulation, we use very simple algorithm. That's why it cannot rely on the complicated issue of global warming, but also meaningful for students to understand about the factor that affect the limit change. This is a sample of simulation, and so the information help you how to use it, and the knowledge behind, and the learning material and feedback we need to use give it to improve the simulation package. This is the control bar. We can control some kind of variable carbon emission, deforestation, and renewable energy use. We can change this, and we can play to see some kind of effects on next decade. If we can see here with 1 degree Celsius, and of course we can train other, and we can observe with kind of it's based on the global temperature and environment. You see, it's best now. It's the increased temperature, which like that. The last one I would like to introduce with you. This is the pendulum simulation. In this, we simulate the simple harmonic motion. This simulation aims to help students understand the simple harmonic motion, like some period, frequency, equation of motion. Due the simulation, students can explore the motion of pendulum influenced by gravity on different conditions like Earth, Moon, Mars, and planet X, and air resistance on the motion of the pendulum. Let's look at the simulation here. The simulation, you can see the simulation. We can see the velocity and time, angle and time graph. You can move it, and the menus. You can see the information of the simulation, how to use the simulation, and the content knowledge of physics, of pendulum in physics, help you understand the concept behind and relevant formulation and the advanced knowledge of pendulum in physics. Help you understand more about simulation. And we also develop learning material for you. You can adapt for your classroom, and we also would like to receive your feedback to help us improve our simulation. In this simulation, we can change variable like pendulum length. We can change the environment like Earth, Moon, or even the planet X. We can change the initial angle or air reason. Now we will look at sample. In that, you can see the real-time graph, the illustrates of the pendulum motion. In this, we set the air resistance. That's why the velocity no change follow time. Now we increase the doctrine of the air resistance. We can see the velocity decrease all the time here. In this simulation, we can observe the graph, and we can change condition like here, reset it, and we can move to on the moon. We can observe the pendulum in the moon condition, and we can see here. We can easily recognize the period increase in this way. Now our simulations package, we also develop some sample of learning material. We upload with the file. You can use it to and adapt it for your classroom. Use the simulation. Next, I would like to introduce you some kind of package. We use AI feedback for help students self-assessment. Help them assess themselves about the knowledge and learn based on the feedback from AI. And next, now you can go to the DigiStem.ai. This is the main project on simulation available here. You can access here. Yes, in every time you can see the simulation package we develop here. You can access detail on the package, and we also assessment for learning. This is physics, geometry. I tell you, and they also student feedback and teacher feedback. Now let's look a little about the physics challenges with AI feedback. Yes, in this topic you can do the topic and this kind of self-assessment. Students go there, they can choose multiple choice format question. In case of if student gets some wrong response, For example, here, yes, they can ask the AI, they can generate and they can feedback for you, for students how to explain why they choose that. And at the end of this challenge, students can receive full feedback from AI. It's very helpful for them to improve what they the witness and they train, help them improve in future.
Dr. Vo Vande has now introduced you to the DigiSTEM website, where you will have a code and you will be invited to take part in our research. And our research then will be under that heading for where teachers can support improvement. So in that website, you're going to find a heading called Teachers Feedback. And what we want you to do is to click in there and to give us the feedback that we need for our research project here, and find and tell us how you found this resource, how you found it. Did you find it useful? Did your students find it useful? Is there any recommendations you can give us as feedback for our research? And also that feedback we will use to improve this package and to keep the simulations going for you into the future.
Now, to teacher to give us feedback, they can go directly to the diffsystem.ie. And in this, we can see teacher. Here we can list here, and we saw our instruction and information sheet. We can do detail there, and we will send you the course, and you can enter the course and continue. And in this side, you can see the questionnaire, and you just identify what you do in the surveys, and then that we would like to receive your comments and suggestions for us to improve our package in the future. Yes, we can, after we finish, we can just net. In the same, we also ask you to ask your student to experience with our simulation to help us improve based on the student voice. You can go the website and find student. You can see the cast like us. You can list the student. Yes, in the website you can see it's near teacher as a student. You can list a student, and you can see instruction and information sheet and everything. And then we can view the course. We will send you the course after training. And in this, we add student can fill some information, very little personal information here, and then student can finish some kind of task here, and then next and submit to us.
So in this final slide, we just want to say thank you to everybody for actually listening to the presentation. We hope that you will come on to our digistem.ie, take part in the simulations, take part in the feedback forum, the teacher feedback, and get your students to complete the student feedback. And do that over the next 2 to 3 weeks, so that we have the research and we have that original research for Ireland and for science and physics education going forward for Ireland, and for improving approaches to teaching physics through digital simulation. Now we will be able to send you out a booklet that we have designed that goes with the project. We'll be able to get you the link and the codes to the website, and we'll be able to also send you hard copies of any of the books we have with science and particularly with physics. If you just email vovande@ul.ie, we'll be delighted to send you out any of those materials to help you and your students enjoy the teaching of physics. Thank you again.